All right, gang, Math 6610, more on ANOVA. What I want to do in this video is dive into the assumptions of ANOVA. The three assumptions for ANOVA are independence, normality, and equal variance. There's going to be a lot going on in this video, so I encourage you to take really good notes, very detailed notes. Number one, it's going to help you on your assignment. Number two, it's going to help you study for your exam. Number three, it's going to help you when you get to the master's thesis component. Most studies implement some type of ANOVA technique. All right, the first assumption is independence. And what independence assumption is, it's not something that we test, but we address independence through random sampling. And we just want to be assured that the measurements in population number one, population number two, all the way up to our kth population are not related. So independence means that our values measurements are not related. So again, let's just jump down. ANOVA is a procedure for testing the equality of K group means, where K is 3 or larger. If K is equal to if K is equal to 2, then we just use an unpooled two-sample t-test. All right, so what I want to do, again, independence, we've talked about that. Let's dive into equal variance. And equal variance has a null hypothesis that we're testing that's very, very similar to ANOVA. We assume that the population variances are equal, and we use sample data to test that. The alternative hypothesis here would be exactly or be equivalent to in the ANOVA alternative. At least one pair of variances are not equal. So the first one I want to demonstrate to you is Bartlett's test. And you'll find that Bartlett's test has more power than the other ones I'm going to show you. And it's really easy to carry out. So we just run Bartlett test. Our Y value, our dependent variable here would be values. And our independent variable is just IND. So when we run this, again, it has more power. More power means that if you hold everything constant, it will produce a lower p-value. So if your goal is to find that you do not have equal variances, you're most likely going to find it with the Bartlett test. So we would report this as the Bartlett chi-square. The test statistic is 5.08, degrees of freedom 2. With a p-value of 0.08. So we failed to reject the null, and we assume that we have equal variances. Please do not say something wacky like we failed to reject the null, therefore our variances are equal. We can't say that. You do not understand the framework and just the basic principles of hypothesis testing when you say goofy stuff like that. It's just not, it's just false. We don't know if this is true or false, and we never will unless we can get all of our measurements from this population and that population and calculate the variances. In fact, we're almost always certain that this is actually a false statement. I mean, what would be the probability that if we were to able to dive into this population, that population, that these variances would turn out to be exactly the same thing? Imagine going out like 17 digits deep and they're all the same. Nah, it's not going to happen. That's really not the point. It's just we're assuming we have equal variances unless sample data, evidence from sample data indicates otherwise. So we can assume that we have equal variances for the sake of testing the ANOVA. Now, Levine's test is a little uh, I don't know, a little strange. First thing, I'm going to show you a lot about Levine's because it's so commonly reported, and there's some common misconceptions about Levine. So I need to access LawStat. Now you should have installed this back in lesson number 1. but I need to access the library for law stat before I can carry out this Levine test. I will show you two different Levine tests and try to teach you the difference. So I need my y again, which is the values, independent, and well, no, I don't want to do that. Let's leave that out for now. So when I run the standard Levine test, what it's going to do, it's going to give me a modified, it's called a Brand Forsyth Levine type test based on the center of the deviation, the center being measured by the median and the absolute deviations being spread around the median. Um, Now, I can change that and let me show you what happens. So if I put location equal, let's just put median just to show you what will happen with this, or we're going to get the same result. 0.3872. However, if I change this to the mean, you'll see that we get something that looks pretty familiar, right? The Bartlett test. To confuse matters even more, I could change this to a trimmed mean. A trimmed mean, typically, you order your data from smallest to largest and you eliminate the top 10% and the bottom 10%, and you focus on the remaining measurements. So if you have any if you have any outliers, you have any extreme values, this will control for their effect. And you notice when you run the trimmed mean that you actually get a p-value somewhere in between. Now, I don't know about you, but I always hate when professors give me choices, right? So what are you supposed to do? Well, I will point out one thing. This is where statistics can get really unethical. For example, let's say that the researcher, for some reason, it's to their advantage to reject the null. Well, then they're going to report and run the classic Levine test using the center as the mean. Why? Because it has more power. It creates, under equal conditions, it creates a lower p-value. What if it's to the researchers uh, uh, to their advantage, to the goals of the study, to not get statistical significance? Well, then I'm going to report the the center as the median. And again, if I circling back, if I want more power, Bartletts is going to be much more sensitive. So yeah, I think we've all probably read the book How to Lie with Statistics, and I forget who said it, but there's three kinds of lies: lies, damned lies, and statistics. This is the way you lie with stats, people. You choose the test that gives you the result that you want. Now, I'm not going to let you do that, so don't get your hopes up. Another thing that we can do, there's another Levine test under the package called CAR, and I really like it because of the following. So it runs a Levine test, and then we run, just like before, we run values, independent, and we can do the center instead of location equal to median. Now, it's going to give us exactly the same p-value and the same test statistic, but I prefer the output because when reporting this, it makes it clear that I'm modeling the underlying probability distribution with the F distribution, degrees of freedom 2, 24, my test statistic, and my p-value. So this would be easy to report. Uh, well, pretend that there's a I can't go in there and do that. All right. So pretend that the 24 has an in parentheses there. Now, another test that we can use is called the Fligner-Collin. And it's easy to run. It's just Fligner.test, same format, values, independent. And you can see that the Fligner-Colleen gives us another p-value of 0.51. So we've run three acceptable, well, with variations, three acceptable uh, uh, tests for the equal variance assumption, and we got how many different p-values? Well, quite a bit. So, drum roll, please. What should we do? Well, first of all, the next thing we're going to do is we're going to dive into the normality assumption. If you can assume normality, I'm going to write this out just so if we can assume normality, then I always want you to report Bartlett. Levine, as it turns out, is more, well, I should probably write this out. I don't want to say this. Let's just say it's more robust than Bartlett's test when our data is not normally distributed. Actually, I should say when our data, when it appears all right, so Levine is more robust than Bartlett's test when it appears that our data does not come from a population that is normally distributed. So when we dive into the normal distribution assumptions, which we're going to do here in just a second, and we can't make that assumption, then we should refer to Levine. The Fligner-Colleen is even, I'm just going to go so we'll say the Fligner-Colleen is even more robust than the Levine test in the absence of normality. Actually, I even consider this to be a non-parametric test. So if we don't have knowledge of an underlying uh, parameter, underlying probability distribution, then, and we see this a lot with Likert data, things that don't again, align with an underlying probability distribution. All right, so probably clear as mud, right? So again, the default here, depending on what we get from the test of normality, is to go with Bartlett, and then we'll report Levine in the absence, or in the presence of, I should say, data that doesn't appear to come from a population that's normally distributed. I really don't want you to report the Fligner-Colleen test. We might run into that once we get into the non-parametric lesson, but for now, I just want you to kind of have that on the back burner. All right, normality. Let's dive into to the normality assumption. The first thing I would want to do with normality is to take a look at the residuals. Now, residuals are just a difference between what we observe and what we predict. And this whole ANOVA process and the procedure and regression all meets out there somewhere. So behind the scenes, under the hoods, if you will, there are these residuals. So since I've created my model, it's been a while, right? I did create the model, right? No, I did not. All right, so we should do that. Let's create the model using the AOV command. Again, we have our values, and let's just make sure that in case we do have multiple data sets open that we tell R which one we're using. So when we get summary of our model, I think we all have tunnel vision on the p-value. So we have statistical significance at the 0.01 level, and we would report this, of course, at 224 equals 8.42, p less than 0.01. So so we run our model. Now we kind of circle back to the assumptions, and specifically for the normality assumption, one of the things I would want to do is look at what's called a QQ plot. And the QQ plot takes a look at the residuals. And so I can do model $ residuals. And let's bring in the QQ line. That helps us visualize. All right, so what we're going to get, shoot, scared me there for a second, is we get on the horizontal axis, we get the theoretical quantiles, and then we get the sample quantiles. I'll teach you far more than you ever care to know about this in Math 5500. But for now, let's just keep it simple in terms of analyzing or getting a graph that helps us analyze, make a decision about the normality assumption. So what we typically do is we look how much deviation from a vertical, this diagonal line, do these points lie. And you will typically not see a lot of deviation in the center. If you do, then you can almost be assured that your normality assumption is not met. But you will see deviation in the tails in the end. So up here, down here, we see some deviation. Now the problem with this is it's a subjective determination. You know, how far away from that line is acceptable? Does this mean that we cannot assume normality? Does this mean we cannot assume normality? Nice picture, gives me an indication that most likely the normality assumption can be assumed, but it's still a subjective determination. So something that we can do that I think is kind of cool, if we'll install the package, and I install these packages prior to posting these videos because sometimes it takes a long time to install. But there's something called GGPU, I should have written this down, GGPUBR, I believe. Yeah, all right. And then there's something called GGQQ plot for model. It works exactly like the others, but it gives us a little better picture, I believe. So what this does, it gives us the same picture as we got, the same graph that we got before. It gives us our theoretical quantiles or sample quantiles, but it gives us these confidence bands around the distribution of points. So now I have more of an objective standard for determining if the normality assumption is met. As long as these points don't fall outside the confidence bands, then we assume that they are close enough, quote unquote, to the line to assume normality. So at this point, and this is something that I would want to include in the write-up, okay? So at this point, I'm I'm kind of checking the box for uh, the normality assumption, right? Um, the the next thing I'd want to look at is the Shapiro test. And let me get rid of this. So for the Shapiro test, I like to look at a couple of different tests. First of all, if I look at the Shapiro test just for the independent variable, I mean, yeah, for the dependent variable, I'm sorry, which are the values. So this is not going to break the values into across professors A, B, and C. This is just looking at the quiz scores for all professors combined. And for the Shapiro test, so eerily quiet. Okay. I can't write and speak. So for the Shapiro test, the null hypothesis is our data comes from a population that is normally distributed. And the alternative is this, the data does not come from a population that is normally distributed. So again, if we fail to reject the null, then we can assume that the normality assumption is satisfied. If we reject the null, then we cannot assume that the normality assumption is met. So overall, we get a test statistic of 0.945, p-value 0.16, so we fail to reject the null, so we can assume normality. Now, something I like to do is I like to dive into the weeds a little bit more here and look at the distribution across Professor A, B, and C separately, because it's quite possible that maybe the scores from Professor A come from a normal distribution, but maybe Professor C scores do not. So we can easily do that by just using the t-apply function. So I want my scores, which again is values across the independent variable, which is listed as independent. And then I can just do Shapiro test. And what this is going to do is going to give me the Shapiro test across each professor. So this this should be for, oh, there we go. This is for Professor A, so we fail to reject. We can assume normality. This is for Professor B. Again, we fail to reject. We can assume normality. And this is for Professor C. We fail to reject. Sorry for the redundancy, but we can assume normality.